Hello class, and thank you for watching. In topic 1.5, polynomial functions and complex numbers part 3, we're going to identify key characteristics of polynomial functions related to zeros when suitable factorizations are available or with technology. And for this particular lesson, we're going to focus on even and odd functions. Identify when a function is even and how that correlates to the symmetry, and when a function is odd and how that correlates to its own symmetry. So let's first define the difference between an even and odd function. An even function is going to be a function that is symmetrical over the y-axis. So that would be across this axis right here. So if I fold it through this line right here, that's going to make the left side and the right side equal to each other. And if you notice that for every x and y that we have, for example, I have the coordinates 2, 3 here, and I have this coordinate down here, 1, -3, I'll notice that on the opposite side, the opposite x coordinate has the exact same y coordinate, -1, -3. Notice that this coordinate has the same y coordinate, but the opposite x's. So opposite x's give us the same y. And the same thing with this one down here. This point and this point have the opposite x's, but the exact same y. So this is the characteristics of an even function. Because of this characteristic, we can determine if a function is even by seeing that if I plug in the opposite coordinate, like if I plug in a +2 and I get a 3, plugging in a -2 will give me 3. And the same thing again with 1 and -1. I get a y value of -3. But not only will it happen again at those points, it's going to happen at all of the points. All of these points right here are going to have the opposite x values as these points over here on the left, but the y values are going to be the same. Now, to prove this mathematically, again, like I said, since every x value and the opposite x value is going to have the same y value, all I have to do to prove this mathematically is if these x values are going to equal to a specific y value, f of x, that means that if I replace my x with the opposite value, which is represented mathematically by using a negative sign, then this equation here should match up again to the one I'm going to end up creating. So let's see what this equals. So -x to the 4th power minus 3 times -x to the 2nd power minus 1. Well, -x to the 4th power is going to multiply a total of 4 negative signs. So obviously x to the 4th is going to be x to the 4th, but the negative sign is also going to be raised to the 4th power. So multiplying 4 negatives is going to make everything positive, since these two negatives are positive and these two pair up to become a positive. A positive times a positive is positive. So the first term is positive x to the 4th power. Now here, we cannot distribute first. The order of operation indicates that we have to first raise this to the 2nd power, and x to the 2nd power is going to be x squared. But multiplying x to the 2nd power, again, that means -x times another -x. And two negatives multiplied together is a positive. So this is going to be positive x to the 2nd power. So minus 3 times a positive x to the 2nd power, and then minus 1. Notice how this equation up here, okay, matched up to this equation right there. Since those two equations are the same, this means that f of x equals to this bottom equation, and this bottom equation is f of -x. Stating that if I plug in a positive number for x, or if I plug in any number for x, positive or negative, and that's going to give me a y value, then plugging in the opposite of whatever this number was, it's going to give me the exact same y value. Okay, so we're going to get that here. Let me move this out of the way. Since f of x is equal to y, sorry, here we go. Okay, and f of negative x is equal to the same y because we got the same equation. Okay, these two things are equal to each other, and this is how we prove mathematically that this equation is going to be an even function, which implies that it's going to be symmetrical through the y-axis. Okay, so this again is the correlation right there, that an even function is symmetrical through the y-axis, and we can prove it like that. Now there's an easier way of proving it when it comes to polynomials, and we'll talk about it right now in a second. Okay, let's look at the second example. Well, an odd function. Now an odd function is symmetrical through the origin. Okay, that means through this point right there. It's symmetrical through that point right there. Being symmetrical through the origin really means that if I rotate this 180 degrees, 180-degree rotation, that it's going to match the current one. So if I highlight this, let me use a highlighter here in blue. Let me trace over it. Okay. And I'm going to get this, and I'm going to rotate it. Let's rotate this thing. Oh, I changed the size. Okay. You see me rotating it. Let me try to get it back to the original size. You see right there, I rotated 180 degrees. So where the left side matches, there you go. See another 180 degrees. Let me just put it over. Notice that the graph matches exactly to its original one. This is something that is symmetrical through the origin. It's equivalent to simply rotating it 180 degrees and the graph matching again to the original one. When we have a type of symmetry like this, that means that we have an odd function. Now, what's the correlation between those points? Well, look at what happens at the points. Let me erase this. Okay. Look at what happens to these points. So let me find points right here. Here we have the point at -1, 4. We have the point 0, 0. Oh, I missed this one. Here's the point -2, 2. And oh, that's it. And we have 0, 0. We have this point right there, which is +1, -4. And then we have this point right here, which is +2, -2. Look at the relationship between the points of x and y. Notice where x is +1 and it has a y coordinate of -4. This one has a y coordinate of +4 when x is equal to -1. And look at this coordinate. Here our x coordinate is 2 and y coordinate is -2, but over here it's the opposite. The x became the opposite and the y became the opposite. So if a function is going to be an odd function, and which implies it's going to be symmetrical through the origin, that means that for every x value that's on the graph, the opposite x and the opposite y value is also going to be on the graph, as you see right here. Okay? And well, how does that correlate again to proving that if a function again is going to be an odd function? Well, we use the same idea, that if I plug in the opposite x, so if I have an x value and I plug in the opposite, I should end up again with the opposite y value, meaning that all of the y values should again become, or the y value should be the opposite. Okay, so let's look at this. So look at this example. Here we have f of x is equal to x to the third power minus 5x. Okay, this is an odd function. To prove that it's odd, I'm going to plug in the opposite x value. So if x is positive, the opposite of a positive is negative, and if x is negative, the opposite, this right here means opposite. The opposite of that negative number will be positive. So let's plug that in. Okay. Well, if raising x to the third power is still going to be x to the third, but the negative sign also has to be raised to the third power, that would be multiplying three negative values. And in this example, this does not equal to positive because only one pair of negatives can make a positive. So these two become positive, and that positive multiplied with this one more negative is going to make the entire number negative. So this is going to be negative x to the third power. And well, this right here doesn't raise anything to a power. It's just going to distribute and multiply these two quantities, and a negative times a negative is positive. So plus 5x. So f of negative x, okay, is equal to this. Notice that these two equations are not the same. This had the x to the third power positive and the 5x term be negative. Notice that they are the opposite values now. The first term is now negative and the second term is now positive. So in relation to this equation up here, f of negative x is equal to the opposite of x to the third power plus 5x, minus 5x, I'm sorry, minus 5x, okay? Notice that if I multiply this with a negative, that gives me negative, and I multiply this negative with a negative, it becomes positive. And this is that right there. So this notation means that I'm getting the opposite of my original function. And this is how you prove that your function is odd. That if I plug in the opposite value of x and I get the opposite equation, as you see right here, all of the terms are opposite, then that means that this function is going to be an odd function, which means that it's going to be symmetrical through the origin. Now, I did mention that there was an easy way to determine if your functions are even or odd without having to do this mathematical analytical part. And that correlates again to the exponents. If all of the exponents are all even numbers, as you see right here, 2, 4, and this last one, even though it's not written, this is technically x to the 0 power, and 0 is an even number because it doesn't have a term, okay? So 4, 2, and 0, all of those numbers are even, then your function is going to be an even function. So f of x is even. This f of x is even. And if you look at the one over here on the right, every single one of these exponents, since there's only two terms, are odd numbers. This number right here is the invisible value of 1, the assumed exponent of 1. Both the number 1 and 3 are both odd numbers. So because both of those are odd numbers, then f of x is an odd function. So this is a very easy way to determine if your functions are going to be even or odd, okay? By simply looking at the exponents. So for example, let's look at example A. Determine if the polynomial are even, odd, or neither, and let's explain why, okay? The easiest way to do and figure out if this is going to be even or odd is by simply looking at the exponent. So since this exponent is 6, this exponent is 4, and this exponent is 2, then f of x is even. So that's it. That's the easiest way to figure out if your function is even or odd. But in order to explain it, you're not going to say that. You can't say that this function is even because the exponents are even. The degree of each term is an even number. That would not be an appropriate explanation. The appropriate explanation would be this. F of x is even because, even though we're not going to do the work, the reason for this is because f of x is equal to f of negative x. That's what's going to happen. When I replace my x's with the opposite x, this is going to simplify back to that. Because this to the 6th power is going to be positive. Since we're going to multiply 6 negative x's, the negatives are going to become all positive. We're going to have an even number of negative x's. And since a negative times a negative is positive, 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 this is all going to simplify to a positive value. So this is going to be 3x to the 6th power minus 7x to the 4th power plus 5x to the 2nd power. So you see, this became that. So, sorry, I fix this on your notes. This should be f of negative x. So you see, f of negative x, which is this, equals to f of x, which is again the original one. So both of them are the same, and this is the reason why f of x is even. F of x is even because f of x is equal to f of negative x. So for this next example, how is this going to be an even or odd function? Maybe neither. Well, let's look at the exponent. Let's do the shortcut first, and let's look at the exponents. Well, here our exponent is 3, okay? Our exponent is 1. That's a 1 right there. And on the last term, this is 1, doesn't have an x because this is x to the 0 power. The exponent here is 0. However, 0 is an even number, not odd. So because we have odd numbers and one even, this is going to be neither. Neither even or odd. So let's prove it, okay? Now, why is it neither odd? The explanation would be simply because, okay, so because, well, f of x doesn't equal to f of negative x, okay? Nor will f of x equal to the opposite of this original function, okay? So this is the reason why. Now let me prove it, okay? And, well, it should be g. Sorry about that. I'm just noticing that I'm calling this g. So it could just match up again to what we originally called it. So g of x does not equal to g of negative x, nor does g of x equal to the opposite of the original one. And let's prove it, okay? It's a very simple way of proving it. Just replace the x with the opposite. So we'll use negative x as the notation, and we're going to get the opposite of whatever the x values that we're using. So negative x to the 3rd power plus 8 times negative x minus 1. So just like the last time, since x is going to be raised to the 3rd power, that'll be x to the 3rd power, and multiplying 3 negative signs together is not going to make it all positive. There's going to be 1 negative times negative times negative. There'll be 1 negative that doesn't pair up with the other 2. Okay, so either that one or the first one doesn't pair up with these two to make it a positive. So there's going to be negative x to the 3rd power. Here there's no exponent, so we're going to just simply multiply negative 8x and then minus 1. So it's close to being the opposite, okay, because this is now the opposite and this is now the opposite. But the last term, because it's in even value, doesn't change it, and we do not get the opposite of the original equation. You see, we do not get the opposite of the original equation. Only the first 2 terms are the opposite of what I started off, but the last term is the same. So it is not going to be odd, and it's obviously not going to be even because it's not the original equation I began with. So this is how we prove mathematically that it is not an even or odd function. But the very simple way is just simply looking at the exponent and seeing that all the exponents are either all odd or all even. And if it's a mixture of even and odd, then it's going to be neither. But in terms of explaining why, well, your explanation would be this. Using the fact that for even functions, the y values have to be the same when you're using x and the opposite. And for odd functions, the explanation would be that for every x, your y value also has to be the opposite as that, okay? So if I plug in the opposite x's, I should end up with the opposite y's. So this is how we prove that, okay? Let's now look on to the next page. So let's use these characteristics and let's use the fact that we have an even or odd function to draw complete sketches of a polynomial. So for number 2, we are stating here that the graph of an odd function is given below on the interval from -6 to 0, as you see right here, from -6 to 0. And use the properties of odd functions to sketch the graph of the function on the interval from 0 to 6. So we want to figure out what is the graph going to look on this end of the graph, okay? Well, since the graph is odd, then this function is symmetrical over the origin, which means that for every x and y value that there is, the graph also has to have the opposite x and the opposite y. So if I look at these coordinate points here, and I'll make a table over here on the left side. If I look at the x and y values over here on the left, let's say here, 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 of course. Oh, there's this one right there also. At -6, -5, -5, -2, -1, -1. And the other ones I'm not going to be able to fit. I'll fit one more, -3 and -2. Since those points are on this side of the graph, okay, those are my x and y values, then because it's symmetrical over the origin, then the opposite x and the opposite y values also have to be on the graph. So if -6, -5 is on the graph, that means that +6, +5 is on the graph. -5, -2 means +5, +2. -1, -1, +1, 1. -3, -2 is +3, +2. And of course this one right here, which I didn't put on my table, oh, this is -4, I'm sorry. Hold on, go back. This is -4, -1. So this would be +4, +1. And then this one right here, that coordinate is -1, -2. So then that would mean that the point 1, 2 would have to be on the graph. So let's plot those points, okay? So 1, 2, 3, 2, 1, 2, 3, still plotting the wrong place. 1, 2, here we go, there we go. 1, 2, 3, 2, I'm going up in that direction. 4, 1, 5, 2, and then 6, 5. And this one goes as high as this one right here, which is around at -2. This point right here looks like where the x value is -2, your y value is around -2.5. So that means that here at +2.5, the y value would have to be at +2, I'm sorry, the y value would have to be +2.5. Which is where I'm putting that point right there. So the graph will look like this. Let's see. Now let's look at the same graph, okay, the same graph, but this time we're going to use the properties of even functions to sketch the graph of the function from 0 to 6. Well, an even function means it's going to be symmetrical. Even functions are symmetrical over the y-axis, which in terms of coordinate points means that for every x and y, the opposite x is going to have the exact same y, which again means this. Okay. So if I have, again, these points here, then the opposite x is going to have the same y. Well, we have those points listed up here, okay? So all of these y's are going to be the opposite for the same x values. So at positive 6, the y value will still be negative 5. At negative 5, the y value is still going to be negative 2. At negative 4, the y value is going to be negative it's going to be negative 1. Where are we? Oh yeah, this point. I forgot to plot this point right there. That's still going to be negative 1. At 3, the y value is still going to be negative 2. At negative 1, the y value is still going to be negative 2. And of course, this one right here, at negative 2, the y value is still going to be the same. So if I connect those points, the graph is going to look like this, which again is symmetrical through the y-axis, through that vertical line. Okay, so there you have it. Now, let's use this concept again to determine missing coordinate values on a table. So let the table below represent an odd function. Again, well, what does that mean? For a function to be odd, it means that for every x and y value that exists on this function, for every x and y, then the opposite x and the opposite y is also going to exist. So even though it's not showing here, okay, like even though it's not showing, if positive 15 and negative 11 are the x and y values on the graph, then that would mean that negative 15 and positive 11 is also going to be a point on the graph. So here, if we know that negative 9 and 13 is on the graph, then that would mean that at positive 9, the y value would have to be negative 13. And if you look at the table, well, we see here at negative 13, what would this number have to be? Well, it would have to be 9, since at positive 13, the x value is positive 9. So the value of b is negative 9. Now, what is the value of a going to be? Okay, well here, when x is equal to negative 3, the y value is a. Well, if x is equal to negative 3, that means that when x is equal to positive 3, it's going to have the opposite y value. So here, at positive 3, the y value is 6. So at negative 3, the a value or the y value here would have to be negative 6, the opposite number. So this is the value of a and b. Let's look at this last example here. Let the table below represent an even function. Well, again, what's the key characteristic of an even function? That for every x and y that's on the graph, then the opposite x is going to have the same y. That's going to exist. That's also going to be, that's also going to be a point on the graph. So as you see here, negative 5, 2. So that means at positive 5, the y value will also have to be 2. Same thing right here. And negative 1, negative 2, no, I'm sorry, negative 2, negative 1, then there has to be a positive 2 that has the same y value of negative 1. So the opposite x is going to have the same value of y. So if we look at the table here, we're looking for the value of a. What is a going to equal to? Well, according to the table, the a value is the y value when x is equal to negative 8. So that means at positive 8, which is right here, the y value is negative 8. Those two numbers would have to be the same. So a would have to be negative 11. And what about this one right here? How do we figure out the value of b? Well, if we look at b, that's the x value, the y value is 2. Well, because this is again symmetrical through an even function, symmetrical through the y-axis, that means that the opposite value of x also has to have the same value of 2. So if I look at the table, when x is equal to -5, the y value is also 2. So these two y values are the same, which means that these two numbers have to be the opposite. The opposite x's give me the exact same y. So this would have to be +5. So there is your values of a and b using the characteristics and the difference between an even function and an odd function. Okay, that concludes again our notes for lesson or topic 1.5, part 3, the polynomial functions and complex zeros. If you have any questions, please send me a message on Remind or through email. And like always, I appreciate you watching and I hope you have a great day. Goodbye.